Hello everyone. So welcome to this particular lecture on electromagnetic induction. In this lecture we will talk about a very important theorem that is called reciprocity theorem. Rather we will try to derive it. So I have no any predefined slides. So basically in this particular lecture we will by hand we will do the complete calculation and we will try to derive or establish this reciprocity relation. All right. Now, reciprocity theorem or the relation of reciprocity, it's nothing but which says that whenever you have two coils or two different circuits and you are wanting to find out the mutual uh, induction coefficient basically, then it doesn't matter in that case which circuit uh, you are changing the stuff. That means current you are changing in which circuit and effect you are seeing in which circuit. This particular thing is immaterial. That means if I can change the current in uh, circuit C1, say for example, and watch the effect on the circuit C2, or vice versa, I change the current in C2 and watch the effect in C1 circuit. In that case, we are going to get the same expression of the coefficient of mutual induction. That's what it basically means. So, in this case, we will consider two different circuits. Say this is one circuit C1, and this is another circuit C2. Let's consider a small current element in this case here, because current is flowing in this particular direction. So this is I1 and this is I2. So once again it will come back, and this is another current element. And let's consider the distance between two different circuits is R. All right, and this distance is such that the R is quite long as compared to the diameters of these two coils, you can say. That means the sizes of these two coils are quite small as compared to this the length R, and that's what is a kind of assumption. So how we are going to proceed? We are going to first find the magnetic field because of this current I1, and that magnetic field will change once we change this current I1. As a consequence to this, the magnetic flux linked with this coil C2 will change, and because of which we get basically a mutual induction coefficient. That's a common thing. So the magnetic field at any point R. Now this is a bit of Biot-Savart law that's we will use. So what Biot-Savart law says, that magnetic field at any point R, according to the Biot-Savart law, the magnetic field at any point R is given by B, that's equal to, sorry, mu naught I by 4 pi integration. This is a closed integral basically, because this circuit is closed, dl cross R divided by R cube. But since we are trying to find out the magnetic field at or magnetic flux linked with the coil circuit 2 because of the change in coil 1, change in current in coil 1, so that is why I am going to write it as B1, which is the magnetic field due to the current I1 flowing in circuit C1, and I'm going to put it as 1 over here. All right. Uh, you may also would like to write a 1 suffix here, because dl1 is the small elementary length that you are considering in the coil C1. All right, and R is basically the vector length, where in the distance where you are trying to find out the magnetic field because of the current flowing through the coil C1. Now alternately, there is a small concept of magnetic vector potential, uh, which is given for this particular circuit as A1. Both are, by the way, these are functions of R. I mean, you need not to write it, but it's already understood. So sorry, mu naught I1 by 4 pi. This first coefficient remains the same. You have got same closed integral, but here in this case you have got dl1 divided by the R vector. So let's consider this equation to be 1, this equation to be 2. So this is the magnetic vector potential. All right. Now, magnetic vector potential, basically briefly, if I have to say, in that case, any field is a vector quantity basically, and there is a potential associated with this field. For example, you have got electric potential associated with electric field, you have gravitational potential associated with gravitational field. Similarly, you have got a magnetic potential, but incidentally it so happens that gravitational potential or electric potential, these are all scalar quantities, but magnetic potential is a vector quantity. So that is why often we call it magnetic vector potential. All right, that's what is the difference in magnetic potential and other potentials. The other potentials are scalar field, but magnetic potential is a vector field. All right. So generally, how do we express that? We express the magnetic potential as some kind of, suppose B is a magnetic field, any unknown magnetic field. In that case, we may write del cross A, where A is the magnetic vector potential of this field B. All right. So we are going to, apply this particular relation also. But before that, what will be the magnetic flux through C2, the coil C2, due to the magnetic field change B1 in the coil C1 because of this current I1? That is basically given by phi 21. Let us write it as phi 21. Why phi 21? Because it is the magnetic flux change or magnetic flux through the coil 2 because of the change in current in 1. That is why I have written in phi 21. That will be given by a surface integral B1 dot ds. Now this is S2. S2 means surface 2. This is surface 1. This is surface 2. If you have some open area bounded by a line, that is nothing but a surface. For example, you have got suppose table surface we talk about. In that case, the perimeter of the table that covers the or that acts as the boundary line which gives rise to a circle. So if any closed line is there, so for example I give you a simple line, it will not give you any surface. But if I close this line somehow, I just take it back like this or any other form and join it back, then you are going to get a surface. So any line which is closed or it closes on itself, that will give you a surface. Similarly, if a surface closes on itself, it will give you a volume like a football. So we are not dealing with volume factors here, we are just dealing with surfaces. So S2 is basically the surface of the coil C2, S1 is the surface of the coil C1, say. So that is why if I take the dot product of the magnetic field B1 due to the coil C1 and take an integral of this dot product of magnetic field B1 with the surface S2, take this dot product over the surface S2. In that case, I am going to get the flux through the surface S2 because of the magnetic field produced by the coil C1. Now, since we know that magnetic field is given by del cross A, so the magnetic vector potential, so I am going to just put it over here, S2, then del cross, say A1 dot ds, which is the small area element in the circuit C2. Now, this is, by the way, the surface integral. This is a surface integral. And we have a theorem which is called Stokes theorem, which says the curl of the surface integral is nothing but the line integral of the vector quantity whose curl is evaluated over the surface or bounding the surface. So this is the magnetic vector potential A1 whose curl you have taken as a surface integral. So you can simply convert it as the line integral over a closed line C2 A1 dot dl2. What is dl2, by the way? Dl2 is a small elementary length of the circuit C2. That means suppose you can consider this is the whole line bounding the circuit C2. If you consider a small part of it and coin it to be dl2, and then all dl2s will make up the complete circumference of C2. All right. So that is the reason why this is by applying the Stokes theorem. Already you have encountered this in your mathematical physics course. So if you have any doubt what is the Stokes theorem, please revisit that once again. So let's consider this to be equation number, say, let's consider this to be equation number 3 and this to be equation number 4. All right. Now, so phi to 1, I am once again writing equation 4. Phi to 1 is basically given by the closed integral over C2 A1 dot dl2. But from equation 2, this is equation 4 which I have written once again. From equation 2 I had a1 to be is equal to mu naught I1 by 4 pi closed integral over C1 dl1 upon r vector by the way. This is equation 2. So if I just put it back to this equation, in that case what I am going to get, that the mu naught I 1 by 4 pi, that will come as a common factor, integration closed integral by the over C1 dl1. So this part I have taken back, this factor I have written as a constant quantity, this is anyway constant. Then you have got the dl1 taken an integral over C1 that I have written over here. Then comes the closed integral over C2. You have got a dl2 over here. So I am going to write it as dl2 by r vector. All right. So this is quite simple. Just I will write this I1 over here. I will keep I1 as it is. Except I1, everything I will write it in a bracket. That means mu naught by 4 pi close integral over C1 dl1 close integral over C2 dl2 upon r into I1. So I know that by the very definition of mutual induction, phi to 1 is nothing but the mu or m to 1 I1. That's what we have got, that whenever you have got flux linked with one circuit changes, or that is directly proportional to the current in the previous circuit. This is the flux associated with the second coil because of the current in first coil. Then I write this relation, and in this case I generally write it as m I1. That's what already we have been writing. Here also I have done the same thing, just I have replaced this whole thing as M21, which is the mutual induction of the coil 2 due to the change of current in 1. All right. So I've got here in this case a new expression for M21, but previously we didn't have any such expression of M21. Here we have got an explicit expression and much detailed expression of M21, that it is nothing but a double integral relation, double closed integral relation basically of the element of length multiplied by the mu naught upon 4 pi. All right. Now, this particular integral is very symmetric between these circuits C1 and C2. That means it doesn't matter whether you alter this integral sign C1 and C2. I mean, in this case, what I have considered that flux linked with the coil C2 is changing because of the current in C1. If you consider the vice versa case, the opposite case, that current in C2 is changing, and because of that there is a flux linked with the coil C1 which is changing, and you want to find an expression for the phi 1 2 basically, you will get the same expression, but you will remain with phi 1 2 as m12 I, say in this case I2, because the I2 will I mean the flux linked with coil C1 will change because of the current I2, or the flux is associated because of the current I2. But these integral you will get to be the same. So you can do it for yourself, you can test it for yourself. So that is the reason why we have got that m12 and m21 to be the same quantity. That means we will get easily that m12 is equal to m21. So this is actually the reciprocity theorem. All right, which actually states, or basically it means that you have got two different coils, and it doesn't matter in which coil you are changing the current and in which coil you are watching the effect. it is all the same. Okay, you are going to get the coefficient of mutual induction to be the same value. So that's what is a reciprocity. That means it doesn't care about where you are where you are making the change and where you are watching the effect. It is all similar, all same. All right, this is all about reciprocity. So it's a very small theorem, a small derivation, very in a not in a direct sense, but in a sort of indirect way, taking into account a lot of integrals, we can come to a conclusion about this particular thing. So that's all I had in this particular video. If you have any doubt or confusion, you may definitely ask me. All right, thank you for watching this video.